So let's kick things off with a pretty wild question. Can a single, really smart piece of code actually replace a massive supercomputer? I mean, the answer could literally change how we solve some of the world's biggest scientific challenges.
Think about it like this. On one side, you've got a supercomputer. We're talking a beast of a machine, costs millions of bucks, and sucks down enough energy to power a small city. But on the other side, you've got an algorithm. What does that cost? Brain power. And its energy use? Well, maybe a cup of coffee. The difference is just staggering, and it leads to a really powerful idea.
What if the answer isn't always about building bigger, faster, more expensive machines? What if we could get the exact same or maybe even better results just by, well, thinking about the problem in a different way? That's the core idea we're going to dig into.
So here's how we're going to break it down. We'll talk about why it's about smarter code, not bigger machines. Then we'll get into the art of asking the right question. And from there, we'll walk through this really elegant three-part framework, defining your goal, choosing your precision, and finding the frontier. So let's jump in.
Okay, first up, the art of the question. And this is so important because it turns out that for some of the gnarliest problems in science, the real challenge isn't writing the code. Nope, it's figuring out what question you're even trying to answer in the first place.
Now, the source material we're looking at here boils this whole art form down into a brilliant, simple three-step framework. It's basically a series of questions that can take a problem that seems impossibly huge and make it something you can actually tackle. It all starts with one fundamental question.
And that brings us to step 1, defining the ultimate goal. This is all about getting crystal clear. Before a single line of code gets written, you have to know, what's the destination? What are we actually trying to do here?
And notice how simple and direct this question is. It's not about how you're going to solve it, it's about what you're aiming for. Are you trying to simulate crystals, molecules? That single choice changes everything that comes next.
So here's the crucial part. This isn't just some philosophical exercise. Answering this question has huge practical consequences. It focuses all your computational power. It tells you exactly which laws of physics or chemistry you need to worry about. And most importantly, it takes the problem from this vague, let's simulate the universe idea, and narrows it down to, okay, let's simulate this specific molecular interaction.
Okay, so once you know your target, you hit step 2, perfection versus precision. And this is where you have to ask yourself, how good does my answer really need to be? It's that classic battle between getting it perfect and getting it done.
The source frames this perfectly. Are you trying to get a perfect atom-by-atom simulation right down at the quantum level? Or is a really good guess, an accurate approximation, actually good enough to achieve your goal?
And this just lays out the trade-off beautifully. An exact simulation, I mean, that's the holy grail, right? But for most complex systems, it's basically impossible with the tech we have now, or even the tech we can see coming. An accurate approximation, on the other hand, gives you results you can actually achieve. The challenge just shifts from an impossible calculation to proving that your guess is reliable. For most real-world science, good enough is the only path forward.
So you've got your goal, you know the level of precision you need. And that brings us to the final step in this framework, finding the frontier. This is all about identifying the wall. Where exactly do our current methods just stop working?
This question really gets to the heart of innovation. It's not just about solving any problem. It's about zoning in on the specific, unsolved, limiting roadblocks. You know, these are the points where brute force computing power just hits a wall, and a smarter algorithm is the only way to get through.
And that's the key takeaway right there. You can't design a clever shortcut until you know exactly what obstacle you're trying to get around. Finding that frontier, that specific limiting problem, that's where the opportunity for a real algorithmic breakthrough is hiding.
So let's put this all together. When you combine these 3 questions, what's my goal, how precise do I need to be, and where's the current limit, you get more than just a checklist. You get a really powerful framework for discovery.
We could call this whole thing algorithmic thinking. And it's not about being some master coder. It's really the art of asking sharp, strategic questions that carve away all the impossible stuff and reveal an elegant, solvable problem right at the core.
Here is maybe the best way to think about it. A supercomputer solves problems with brute force. It's kind of like trying to find a destination by driving down every single road in the entire country. But a smart algorithm, guided by these precise questions, that's like a GPS. It just calculates the one, single, most efficient route to get you exactly where you need to go.
So in the end, it really does seem like the potential to replace a supercomputer doesn't lie in a faster chip, but in a better question.
It proves that the right question asked at the right time can be far more powerful than the biggest machine on Earth. Which really only leaves one thing to consider. What question will you ask?